Now let's discuss the properties of arrays. But first, to review, we know that an array is a contiguous block of data. We know it's stored the same way in RAM. It's stored as a contiguous block of data. Now with any data structure, the two most common operations are reading to the data or writing to the data. We're going to first handle the simple case, which is reading the data. Let's suppose we want to read the first element of our array. Well, as a programmer, we have an array. Let's say we allocated it by calling it myArray. So this is a variable that we have. To read the first element, the intuitive thing is to go in memory at the first address and then read the value. Now that's exactly what's happening under the hood, but we as programmers don't need to know the exact address of every single value. As we use the array, we use indexes to access values. The first value is always at index 0, not at index 1. That can be confusing if you're a beginner, but it's always starting at 0. The next one is at 1, and the next one is at 2, etc., etc. So when we read the first value, which is at index 0, it's automatically going to go to this location in our memory and read the value that's stored in memory. Since we can automatically map any index in our array to a location in memory, that means we can instantly read any value as long as we have the index for it. To represent that that's an efficient operation, we call it big O of 1. We're going to talk more about big O notation later in the course, but for now, what this means is that in the worst case, to read a value, assuming we have the index, so suppose we want to read the value at index 2, it's an instant operation. It happens in constant time. No matter how big our array gets, if we want to read any value in the array, we can read it instantly. That's what big O of 1 means. At least that's the oversimplified explanation so far. The fact that we can go to any arbitrary address in our RAM and then read the value at that address is a property of RAM. It's actually in the name itself. Random access memory is what RAM stands for. It basically means we can randomly access any portion of the memory in constant time. Suppose if we wanted to access this value, we don't have to start from the beginning of our RAM and then keep looking for it. We can automatically access it. And that's pretty important, as you can tell, because if we have a lot of RAM, we don't want to have to go through the entire RAM every single time. If we want to access the third value in the array, we don't want to have to go through the first and second values because it's not necessary for us. Now, after we read our first value, next we want to read the second value and the third value and keep doing that until we get to the end of the array. That's pretty easy. We know that the first index we start at is, let's say, 0. I'm going to call it I. In code, we would typically say myArray at index I to read the value. And then, of course, we would increment the I to be 1, and then we would increment it to be 2, and we would keep doing that until it equaled the length of the array, and then we would stop. So essentially, we would loop through the entire input array. In most languages, you can do so with a for loop or a while loop. Now, while this might seem really simple, the ideas that we're talking about now are going to be the building blocks for very advanced algorithms we talk about later in the course. So we talked about reading from an array. Now it's time to talk about writing to an array, which is going to bring us to an important properties of arrays, which is that they're of fixed size. In this case, we declared an array of 3 values. It's fixed size. Suppose we want to add a 4th value to it, let's say a 7. Well, taking a look at our model of memory, so the simple thing to do would just be add a 7 in memory, but we have to make sure it's contiguous, so we would do so only at address 12. So then we have an array of size 4, and it's still contiguous. This seems like it might work, but the way RAM works, we don't always get to decide exactly where we allocate our RAM. We don't always get to decide exactly where we store our values. And we don't know for sure that this spot in RAM is even available for us. It could be that we already have maybe another array stored over here, or maybe the operating system is using this part of our memory for some other purpose. So we're not necessarily allowed to put the 7 over here. Okay, then you might think, well, let's just let the operating system decide. Just put a 7 anywhere in memory. But if we do that, we don't follow the property of arrays. It's no longer contiguous. Now we have 2 arrays. That's not what we wanted. We wanted a single array, because if we do it like this, and then let's say I'm looping through this array, I'm at index 2, now I increment and I'm at index 3, what we're going to try to do by accessing this is we're going to go to this spot. But we don't know that the 7 is stored over here. It might be stored somewhere else. So this is going to break. Basically, we've come across the biggest limitation of arrays, at least for static arrays, which is what we've talked about so far. Static arrays basically mean that they're fixed size arrays. So before we continue to discuss the limitations of static arrays, I do want to mention, if you're used to a programming language like Python or JavaScript, you might have never come across this limitation because those languages don't really offer static arrays. You never have to worry about running out of space when you're using an array. And that's because those languages usually offer dynamic arrays as the default, which we're going to discuss later on. So suppose we allocated an array of size 3. Initially it's empty, but there has to be something stored here. And usually by default, languages will initialize it to be all 0, or sometimes they won't initialize it at all. And sometimes there can just be some random values here, like just some random arbitrary values that we didn't even put there. So initially we have some space. Let's say we start adding values to it. We add a 5, that puts a 5 in memory. We add a 6, that puts a 6 in memory. We add a 7, that puts 7 in memory. Now we're allowed to remove values, but when we say remove, we can't actually delete this in memory. We can't deallocate that with a static array. When we say remove a value, we're basically saying we're going to overwrite it by putting, let's say, 0 in that case. And we would say that this value is no longer relevant. We have a 0 here. We only care about these two. This is still in memory, but we don't care about it. And we can, remove all the values in a similar way. But what we can't do is add a new value. By the way, as we add a new value to the end of the array at the next empty spot that we're keeping track of, it's also going to be an instant operation because we know this is index 0, this is index 1. We want to write to this position. Therefore, we know instantly that we're writing to this position in RAM. So writing to any position is also a big O of 1 operation. It's constant time. We can think of it as an instant operation. Similarly, removing a value is also as efficient as big O of 1. It's a constant time operation because what we're really doing is just going to that position in memory and Xing it out. We could be replacing it with a 0 or a -1 or something like that. We're not actually deleting it, but we're overwriting it. So these are the efficient operations with a static array. So we have a couple values in our array, and remember, these are ordered values. The 5 comes before the 6. We know that because of the way the indexes work. So let's say we wanted to arbitrarily insert a value into the middle of the array at any position in the middle of the array. By that, I mean any position in between these values, at the end of these values, or at the beginning. We know inserting at the end is always efficient because we're inserting into an empty spot. If at least there's one available. We're assuming that there is space available. That's efficient. That's O of 1. But inserting at any arbitrary position, like the middle or at the beginning, is not going to be efficient because let's say I want to insert the value 4 at this position. Now, it's easy enough to overwrite the value with a 4, but then we have a 4 and a 6. What we actually want is to have 4, 5, 6. We could put the 4 over here because that's efficient. It's O of 1 and there is space there, but that doesn't achieve 4, 5, 6. We have the elements out of order. With arrays, including static arrays, the order of the values does matter. So for us to insert the 4 over here, we first have to shift the 5 to the next position. But if we shift it over here, we're going to get rid of the 6. That's not what we want to do. So before we shift the 5, we have to shift the 6, and then we shift the 5. In other words, we're going to take the 6, it's at index 1, but we're going to set it to be index 1 plus 1, meaning it's going to be at index 2. So the 6 is going to go there. The same thing with the 5. It's going to go at index 0 plus 1, which we know is 1, so it's going to go here. Only after we've performed this shifting are we allowed to put the 4 over here. There's space for it now, and we preserved the order of the values. The downside of this is we couldn't do it in a single operation. We had to move every value in the array. In this case, we only had 2 values in the array. But imagine if we had a really long array and it was all filled with some values, and we wanted to insert a value at the beginning, then we'd have to take all of these, shift them, and then we could insert the new value. This is not very efficient. That's what I'm getting at. We call this a big O of n operation. N in this case refers to a variable, and in this problem, n refers to the number of elements in the array. We can call that the length of the array. Length meaning the actual values we have, not the size of the array, but the number of values. And I've been using big O, but what it actually means is the worst case. Because this, what we just did right now, was the worst case. What we had to do is we had to shift every value in the array, which means n values, over to the right by 1, and then we were allowed to insert the new value. But if we were inserting in the middle between 5 and 6, let's say what we actually wanted to do was have a 5 and then a 4 and then a 6, then we wouldn't have had to shifted the 5 at all. We would only have had to shift the 6. The 5 would have stayed over here on the left, and we would have inserted the 4 over here. So in that case, we would have only needed to shift one value, not every value in the array. But we don't want to go through every possible scenario, so we generalize it. We say in the worst case, if you're inserting a value in the middle of the array at any arbitrary position, in the worst case, we might have to shift every value. We might have to shift n values. So in the worst case, the time complexity is going to be big O of n. And the exact same thing is true if we're removing a value at any arbitrary index. When I say removing, I'm not just saying, replacing it with a 0 or something. I'm saying I want to pretend like this doesn't exist anymore. I want the first value to be 6. In that case, we would do something similar, but we would take the 6 and then shift it to the left by 1. So we would say 1 minus 1 is going to be 0. So we're going to put it at the 0th index. 7 is at index 2. We're going to take 2 minus 1, which is 1, and we're going to move this to that index. In the end, we're left with a 6, 7. Technically, the 7 from over here would still be there, or we could have replaced it with a 0, or we could, do something to pretend like it doesn't exist. But the memory that we actually allocated here definitely does exist, and it would be reflected in RAM. So to summarize the operations for a static array, reading or overriding the ith element of an array. Ith basically means any arbitrary element. You could pick any index and read or write from it. You can do that in big O of 1 time. You can do that in constant time. To insert a value at the end of the array or to remove the value at the end of the array is also a big O of 1 time operation. That's assuming that we have an empty space left at the end, or we at least have one element at the end for us to remove. Now, inserting into the middle of an array in the worst case is going to be big O of n. For an empty array to insert in the middle, it would be very efficient. It would be big O of 1. But we know we're talking about the worst case. That's what big O refers to. To insert in the middle would be big O of n. We might have to shift every value in the array. The same thing for removing in the middle. We might have to shift every value in the array.